how can we verify Ohm's law? For a conductor, if we can show that the ratio of potential difference across its ends to the current flowing through it is a constant, then we can verify Ohm's law. Alternately, if we draw a graph between the potential difference applied across it and the current flowing through it, and if that is a straight line, then also we can verify Ohm's law. To verify Ohm's law in laboratory, we can connect a conductor of resistance R to a source of potential difference, say a battery, through a rheostat and a key, and we can also connect an ammeter in series with the circuit and a voltmeter parallel to the given conductor. S be the switch key, B the battery, R is the rheostat, A here represents the ammeter, V represents the voltmeter. As we had discussed earlier, a voltmeter is always connected parallel to the points across which the potential difference is to be measured, and an ammeter is connected in series with the circuit where the current is to be measured. By using the rheostat, we can easily vary the resistance. The switch key is closed, so a current flows through the circuit. Using the rheostat, the current is made minimum. Now, by adjusting the rheostat, the potential difference across the resistance is increased gradually by small amounts so that the corresponding current is noted. If you are getting a graph between V and I as a straight line represented like this, then Ohm's law is verified. If you don't need to draw a graph, you can obtain the ratio of V to I from the noted values, and if it is found that it is a constant, then also Ohm's law is verified. The factors affecting the resistance of conductors. The factors affecting the resistance are the length of the conductor, its cross-sectional area or thickness, the nature of material, and the temperature. It has been observed that the resistance of a conductor is directly proportional to its length. That means, for a conductor, when the length is doubled, the resistance becomes double. When the length is tripled, the resistance also gets tripled. And if it is half, then again the resistance becomes half. So the resistance of a conductor is directly proportional to the length of the conductor. Also, it is observed that the resistance is inversely proportional to the cross-sectional area of the conductor, which implies that if the cross-sectional area is double, resistance becomes half, and vice versa. The electrical resistance also depends on the nature of conductor. Some materials have low electrical resistivity while others have high electrical resistivity. For example, if we take wires of same physical dimensions and of different materials, that means say copper, manganese, silver, etc., all having equal length and cross-sectional area, the resistances will be different. Since electrical resistance is directly proportional to the length of the conductor and inversely proportional to the cross-sectional area, combining we can write R proportional to L over A. So this can be equated as R is equal to rho L by A. The constant of proportionality, rho, is known as the electrical resistivity of the material. It's also known as specific resistance. The electrical resistivity, rho, can be written as R A by L. If the cross-sectional area is 1 meter square and the length of the conductor is 1 meter, then we can say that the resistivity of the material is numerically equal to its resistance. The SI unit of electrical resistivity is ohm meter. It comes from ohm meter square divided by meter, so ohm meter. The electrical resistivity is numerically equal to its resistance for a conductor of cross-sectional area 1 meter square and length 1 meter. For a conductor of unit length, that is 1 meter, and unit cross-sectional area, that is 1 meter square, it is a cube of side 1 meter. So we can say that a material's electrical resistivity is numerically equal to its resistance when it is made a cube of unit length. It is to be always noted that electrical resistivity is independent of the physical dimensions of a material. For a material, electrical resistivity depends only on the temperature, and also it varies from one object to another. So we can say that electrical resistivity depends on the nature of the material as well as the temperature. For metallic conductors, electrical resistivity increases with temperature. Electrical resistance is dependent upon the physical dimensions of a conductor, that is the length and cross-sectional area. As the constant resistivity of metallic conductors rises with temperature, so does the resistance also increase with increase in temperature for metallic conductors. The table shows the electrical resistivities of some common substances. Here we can find that the resistivity of copper is 1.69 into 10 raised to minus 8 ohm meter. Now by saying that the resistivity of copper is 1.69 into 10 raised to minus 8 ohm meter, we mean that if we take a rod of copper metal 1 meter long and 1 square meter in area of cross section, then its resistance will be 1.69 into 10 raised to minus 8 ohms. It should be noted that a good conductor of electricity should have a low resistivity and a poor conductor of electricity will have a high resistivity. From the given data, we find that of all metals, silver has the lowest resistivity, that is 1.6 into 10 raised to minus 8 ohm meter, which means that silver offers the least resistance to the flow of current through it. The silver metal is the best conductor of electricity. It is obvious that we should make electrical wires of silver material, but silver is very costly. We use copper and aluminum wires for the transmission of electricity because copper and aluminum have very low resistivities, due to which they are very good conductors of electricity. The resistivities of alloys are much more higher than those of the pure metals. For example, resistivity of manganese, which is an alloy of copper, manganese and nickel, is about 25 times more than that of copper, and the resistivity of constantan, which is an alloy of copper and nickel, is about 30 times more than that of copper metal. It is due to their higher resistivities that manganese and constantan alloys are used to make resistance wires or resistors used in electronic appliances to reduce the current in an electric circuit. Another alloy having a high resistivity is nichrome. The heating elements or heating coils of electrical heating appliances such as electric iron and toaster, etc., are made of an alloy rather than a pure metal. That's because the resistivity of an alloy is much higher than that of pure metal, and an alloy does not undergo oxidation. On the basis of their electrical resistance, all substances can be divided into three groups: good conductors, resistors and insulators. Those substances which have very low electrical resistance are called good conductors. A good conductor allows the electricity to flow through it easily. Silver metal is the best conductor of electricity. Copper and aluminum metals are also good conductors. Electrical wires are made of copper or aluminum because they have very low electrical resistance. Those substances which have comparatively higher electrical resistance are called resistors. The alloys like nichrome, manganese and constantan all have quite high resistances, so they are called resistors. Resistors are used to make those electrical devices where high resistance is required. A resistor reduces the current in a circuit. Those substances which have infinitely high electrical resistance are called insulators. An insulator does not allow electricity to flow through it. Rubber is an excellent insulator. Electricians wear rubber hand gloves while working with electricity because rubber is an insulator and protects them from electric shocks. Wood is also a good insulator.